In this video, we'll focus on two-dimensional tensors. We'll see some examples of two-dimensional tensors, 2D for short, tensor creation in 2D, indexing and slicing in 2D, and we'll go over some basic tensor operations. A 2D tensor can be viewed as a container that holds numerical values. Consider the following database of housing information. Each column contains a feature or attribute, such as number of rooms, the age of the house, and the price of the house. Each row represents a different house. We can represent this data with the tensor X. In 2D, tensors are essentially matrices. Each row of the tensor corresponds to a different sample, and each column represents a different feature or attribute. We can represent grayscale images as 2D tensors. The image intensity values can be represented with numbers, the number 0 being black and 255 being white. These numerical values are stored in a grid. Like a database, we can store them as a tensor. Tensors can be extended to 3 dimensions, 4 dimensions, and so on. The math for these operations gets a little difficult, so we'll only focus on 2D tensor operations, analogous to matrix operations. Let's show some applications of 3D tensors that you'll most likely see. Some color images are composed of 3 color components, or channels: the blue channel, the green channel, and the red channel. Like grayscale images, each of these color components or channels is made up of different intensity values. We have the blue channel values, the green channel values, and the red channel values. Each of these channels can be stored in a 3-dimensional tensor. Now let's review tensor creation in 2D. Consider the list A. The list contains 3 nested lists, each of equal size. Let's color code them for simplicity. We can cast a list to a torch tensor as follows. It's helpful to visualize it as a rectangular tensor or matrix. Each of the nested lists corresponds to a different row of the matrix or tensor. Consider the following list. We can use the method ndim to obtain the number of axes or dimensions, sometimes referred to as the rank. The first list represents the first axis. This list contains another set of lists. This represents the second axis or dimension. The attribute shape returns the number of rows and columns. The first element corresponds to the number of rows in the rectangular representation, in this case 3. The second element corresponds to the number of columns, in this case 3. The convention is to label the vertical axis axis 0 and the horizontal axis axis 1. We can use the method size to obtain the number of elements in a tensor. We see there are 3 rows and 3 columns. Multiplying the number of rows and number of columns together, we get the number of elements, in this case 9. Now let's discuss indexing and slicing in 2D. We can use rectangular brackets to access the different elements of a tensor. The following image demonstrates the relationship between the list representation and the indexing convention. We can also use the rectangular representation. The first index corresponds to the row index, and the second index corresponds to the column index. We can also use a single bracket to access the individual elements in the tensor. Let's see some examples. Consider the following syntax. This index corresponds to the second row, and this index corresponds to the third column. The value obtained is 23. Consider this example. The first index corresponds to the first row. The second index corresponds to the first column. The value is 11. We can also use slicing in PyTorch. The first index corresponds to the first row. The second index accesses the first 2 columns. Here are the following values. Consider this example. The first index corresponds to the last 2 rows. The second index corresponds to the last column. Let's discuss some basic tensor operations in 2 dimensions. We can add 2 tensors. The process is identical to matrix addition. Consider the tensor X. Each element is colored differently. Similarly, consider tensor Y. Each element is also colored differently. We can add the 2 tensors. This corresponds to adding the elements in the same position together, i.e., adding elements contained within the same color boxes together. The result is a new tensor that is the same size as tensor X and tensor Y. Each element in the new tensor is the sum of the corresponding elements in tensor X and tensor Y. In PyTorch, we can add 2 tensors as follows. We define the first tensor X. We then define the second tensor y. We then add the tensors. The result is identical to matrix addition. Multiplying a tensor by a scalar is identical to multiplying a matrix by a scalar. Consider the tensor y. If we multiply the tensor by the scalar of 2, we simply multiply each element in the tensor by 2. The result is a new tensor of the same size, where each element in the tensor is multiplied by 2. We can multiply a tensor by a scalar in PyTorch as follows. We define the tensor y. We then multiply the tensor by a scalar and assign it to the variable z. The result is a new tensor where each element is multiplied by 2. Multiplication of two tensors corresponds to element y's product or Hammurabi product. Consider the tensor x and the tensor y. The element y's product corresponds to multiplying each of the elements in the same position, i.e., multiplying elements contained in the same color boxes together. The result is a new tensor that is the same size as tensor x and tensor y. Each element in the new tensor is a product of the corresponding elements in x and y. In PyTorch, we can multiply two tensors as follows. Consider the tensor x and tensor y. We can find the product of the two tensors x and y and assign it to the variable z as follows. We can also perform matrix multiplication with a tensor. Matrix multiplication is a little more complex, but let's provide a basic overview. Consider the matrix A, where each row is a different color. Also consider matrix B, where each column is also a different color. In linear algebra, before we can multiply matrix A and matrix B, we must make sure that the number of columns in matrix A is equal to the number of rows in matrix B. In this case, they're both 3, so we can proceed. For matrix multiplication, to obtain the ith row and jth column of the new matrix, we take the dot product of the ith row of A with the jth column of B. For the first row and first column, we take the dot product of the first row of A with the first column of B, as follows. The result in this case is 0. For the first row, second column of the new matrix, we take the dot product of the first row of matrix A, but this time we use the second column of matrix B. In this case, the result is 2. For the second row and first column of the new matrix, we take the dot product of the second row of matrix A with the first column of matrix B. The result is 0. Finally, for the second row, second column of the new matrix, we take the dot product with the second row of matrix A with the second column of matrix B. The result is 2. In PyTorch, we can define the tensor A and B as follows. We can perform matrix multiplication and assign it to the tensor C. The result is a new tensor C corresponding to the matrix multiplication of tensor A and B.